In this video we'll be solving right triangles, and there are exactly 6 basic things to know about any triangle. That is the 3 sides and the 3 angles. That's what makes up any triangle. So when we solve it, that means determining the other 3 things. So typically we'll be given 3, some combination of 3 of them, and we need to find the other 3. So the conventional way to name the 6 parts of a right triangle, we need to know this. So if we draw out the right triangle here, and we'll name it ABC, triangle ABC. So you notice the angles have capital letters, and then the sides that go with them, so this would be side A over here, this would be side C over here, and this would be side B over here. The sides are lowercase. And notice that the angle A faces side A, angle B opens up to side B, and angle C, the hypotenuse, opens up. The 90-degree angle opens up to the hypotenuse. And it's common in a right triangle that C will always be your hypotenuse. So A is opposite of angle A, B is opposite angle B, side C is opposite angle C. So again, sides are lowercase, angles are uppercase. Okay, this next section here, to solve right triangles, make use of the following facts. Theta is one of the non-right angles. So sine theta is opposite over hypotenuse. You know all that already. We've worked on that. So we had this little saying, SOHCAHTOA, and that's just an abbreviation for this. And the sum of the interior angles in a triangle, so they all add up to 180 degrees, or in radians, pi radians. Pi radians is the same thing as 180 degrees. So let's move to example 1 next. Alright, so example 1, triangle ABC is a right triangle. They tell us that. All of these in this lesson will be. They tell us that angle A is 32 degrees 30 minutes and side C is 122. So we know that this is angle A because, well, one, it's in degrees and minutes here, and then also it's a capital letter. And then side C here is a lowercase letter, so we know that means it's the side. So the way we draw it isn't going to matter. I'm going to draw it like this. You could draw it reversed. You could, for example, draw it like this. You could do that with this side here, but I'm choosing to do it this way. So 90-degree angle here. This would be angle C, angle A, angle B. That's the way I'm labeling it. And this would be 32.5 degrees. I'm going to go ahead and do that work. 30 minutes is half a degree because there's 60 minutes in 1 degree, so that's 32.5 degrees is the same thing as 32 degrees 30 minutes. And angle C is going to be our right angle. We know that we have a right angle in there because it's a right triangle, and then the hypotenuse here would be 122. So angle B is just going to be equal to 180 minus 90 minus 32.5. Okay, and then when you do that work, you're going to get 57.5 degrees. So there's that part. So we now have all 3 angles, 57.5 degrees there. And now we just need the side lengths. So to do that, we're going to set up our SOHCAHTOA. So sine, it doesn't matter, we can use many different combinations of the trig function. So I'll use sine of the 32.5 degree angle is equal to the opposite side, which is little a, I should label that, this is little a, over the hypotenuse, which is 122. So side A is equal to 122 times sine of 32.5 degrees. I should put that in parentheses there. So let's bring up our calculator here, and I'm going to pan this over a little bit so we can see our work here. So 122 sine of 32.5 degrees. Hit enter. Now we get 107. We need to make sure we're in the correct mode. We are in radian mode. That's not going to work. We need to make sure we're in degree mode in our calculator. So I'm going to reevaluate that now, and we get 65.55. So side A is equal to 65.55. So we'll label that here, equals 65.55. So now we have 2 sides and all three angles, so we just need one more side. So this time I'm going to use cosine. So cosine of the 32.5 degree angle is equal to the adjacent side. This one right here would be adjacent. That's side B. So little b over the hypotenuse, 122. So little b is equal to 122 times cosine of 32.5 degrees. So in my calculator, I can actually just highlight this, come over here and get on top of the sign there and just hit cosine and shortcut that a little bit. So that gives me 102.89. So little b is 102.89. And now we have this triangle solved because we have all three sides and all three angles. And now here in example 2, we have a right triangle. They give us side B. So we need to find side A here. We need to find side C here. And we need to find angle A right here. So notice this is in radians. So 0.81 radians, this would be pi over 2 radians right here. To write that small. 90 degrees, same thing as pi over 2. They're using radians, so we need to use radians. So there are 180 degrees in a triangle, and there are pi radians in any one triangle. If you add up all of the angles, they would sum to pi radians. So I have this. I have pi minus 0.5 pi, or pi over 2, right? Minus 0.5 pi, same thing as pi over 2. Make that pi. So 1 pi minus half a pi minus 0.81 radians gives me 0.761 radians left over. So angle A is equal to 0.761 radians rounded. Okay, so I'm going to put the 0.761 right here. So again, there are pi radians. So I took pi radians minus pi over 2 radians. In my calculator, I just used 0.5 pi minus 0.81 radians. So this the total radians in any triangle, pi, minus this angle, pi over 2 radians. Subtract that angle, 0.81 radians, and we were left with the 0.761 radians. So that's what we did there. Okay, now we have all three angles. Now we need the missing sides. So we need to make sure our calculator is in radian mode before we go any farther. Okay, so I know that I have this 0.761 angle. I know I have from this angle, I have the adjacent side. I want the hypotenuse. So adjacent and hypotenuse is cosine. So cosine of 0.761 radians is equal to the adjacent side, 16.3, over the hypotenuse, little c. This is probably should write that smaller. This is, I intended for that to be a lowercase c. I'll write it a little smaller there. So if we just put this over 1 and cross multiply, we get 16.3 equals c cosine of 0.761 radians. So then we divide by cosine of 0.761 radians on both sides. And finally we have little c is equal to 16.3 divided by cosine of 0.761. We're already in radian mode, so this is okay to do. Divided by cosine of 0.761. Close that parentheses, and we get 22.5. So little c is equal to 22.5 equals 22.5. There we go. And lastly, we need side A there. Now we just need to find side A. That's all that we're missing is side A at this point. So I can use either the 0.81 radians or the 0.761 radians. It doesn't matter. I'm going to choose to use this one. So from that angle, the side A is my opposite side, and I have the adjacent side, 16.3. So I'm actually going to use tangent this time. I could use sine because I want the opposite and I have the hypotenuse, but I'm choosing to use tangent because I have the opposite, or I want the opposite and I have the adjacent. So tangent is what I'm going with. Tangent of 0.761 radians equals opposite little a over adjacent 16.3. So little a equals 16.3 times tangent of 0.761. So we need to be in radians, and we already are. So we can just type this in, tan of 0.761 radians, and we get 15.52 rounded. So little a is 15.52. So we'll put that right here, and that triangle is solved. We have all three sides, all three angles, so we are done. All right, so we have a lot of reading that we can go through here, but basically this paragraph here is telling you that sometimes you only have the right angle and you're missing the other two angles, but you are given at least two sides. When that's the case, you're going to use the sine inverse or cosine inverse or tan inverse. So that would be second sine, second cosine, second tan to find those angles. That is called sine inverse, cosine inverse, tan inverse, also arc sine, arc cosine, arc tan. It is used, you use those to find angle measures. We use regular sine, cosine, and tangent when we're finding side lengths. When we want to find angle measures, we use the inverse, sine inverse, cosine inverse, tan inverse. Don't get that confused with secant being the reciprocal of cosine. Okay, don't get that mixed up. We are going to use second sine, second cosine, second tan on our calculator when we're finding angle measures. Okay. Now let's apply that information to example 3 here. So it says triangle ABC is a right triangle. A is 4, B is 9. So we'll make a sketch first thing. This. So this is A, this is B, and this is C. So it's a right triangle, so we know C is a 90-degree angle. And side B is 9. Use another color here. Side B is 9. Side A over here is 4. So side C is going to be equal to, we're just going to use the Pythagorean theorem here. So C squared equals A squared plus B squared. So C is equal to the square root of little a squared plus little b squared. So put that in our calculator. 9 squared plus 4 squared, and we get 9.85 approximately. So this side is 9.85. So now we have all three sides, and we know that one of our angles is 90 degrees. Now we need the others. So this is where we can use those inverse trig functions. So, for example, if I want to find angle A, I can use sine inverse in order to do that. So sine of angle A is equal to opposite 4 over hypotenuse 9.85. So that means that A is equal to sine inverse of that amount, 4 over 9.85. So again, when we're finding angle measures, we'll use the sine inverse. So second sine inverse of the opposite side, 4, divided by the hypotenuse, 9.85. And we get approximately 0.41817. So that doesn't make any sense, right? So let's go in here to mode and get in the correct mode so that we're in degrees. So if you notice, if you get something that makes no sense, there's no way that angle is 0.418 degrees. So now reevaluate that in the proper mode, and we get 23.96. That makes a lot more sense. So always check your answers there. And then if we want to find angle B, sine of angle B is equal to the opposite side, 9 over hypotenuse 9.85. So that means that B is equal to sine inverse of that amount, 9 over 9.85. Again, when you're finding angles, you use sine inverse. When you're finding sides, you use regular sine. So second sine inverse of 9 divided by 9.85. We're in degree mode. We fixed that before. 66 degrees. So we'll put that right here. And we're done. We have all three sides, all three angles. So we can now move on to example 4. All right, so some more reading to do here. We use sine inverse above. We could have used cosine inverse tangent as well. And you just need to know that depending on the side lengths, the sides that you have and the angle you want will determine which trig function is most appropriate. In all of the previous examples, we produced approximate answers, but we can often get exact answers when, well, we can get exact answers when we have special triangles with 30, 60, 90, and 45 degree angles, or their radian equivalents. And if you recall in the previous unit, we worked with our special 30, 60, 90, and 45, 45, 90 special right triangles, and we were able to get the ratios, and we're actually going to apply that now. So let's look at example 4 here. So triangle ABC, so draw that. I just usually draw the same exact triangle every single time, and that's always okay. So ABC, so side C is 17, angle B is 45. Obviously, this is a right triangle, so this is 90. That means 90 minus 45 minus 45, we would do 180 minus 90 minus 45. And let's try that again. 180, subtract 90, subtract 45, and we'll get 45. You probably know that already. Another shortcut is if you know you have a right triangle, just take the one angle that you do have and subtract it from 90, because, and you'll get the same answer, because these two angles have to equal 90, because this already equals 90 of the 180. So hopefully that makes sense to you, but that's a little bit of a shortcut that you can use. So now we know all of this. Sometimes it's good to make a list. We know angle B, angle A, angle B, angle C. A is 45 degrees, B is 45 degrees, C is 90 degrees. And we know that side C is equal to 17. So we have that information. We just need to find A and B. Now, if we apply our special right triangle here, we'll just make a quick little sketch of that to refresh your memory. So in our 45, 45, 90 triangle, our sides were 1, 1, and square root of 2, like this. So now we can recall that, for example, sine of 45 degrees was equal to the opposite. So if I'm using this angle, the opposite would be 1. The hypotenuse would be square root of 2, and we fixed that. We rationalized it as square root of 2 over 2. In similar fashion, cosine of 45 is from this angle, for example, is equal to the adjacent over the hypotenuse. So when you rationalize that, you get the same thing, so square root of 2 over 2. And we're going to use that information in just a moment. So let's find side B first. Let's find this lowercase b here. So we're going to find a side length, so we're going to be using regular sine this time. So sine of 45 degrees, if we're using this angle here, is, or actually we'll use this one, is equal to the opposite side, little b, opposite side over here, little b over 17. So little b is equal to 17 sine of 45. Well, we know the exact value of sine of 45. We found it up here. So little b is equal to 17 times the exact value of sine 45 is square root of 2 over 2. So we fix that, and we get little b is equal to 17 square root of 2 all over 2. We just multiplied 17 times square root of 2 over 2. So let me do that right here. 17 over 1 times square root of 2 over 2 gives us 17 square root of 2 on top, 2 on the bottom. All right, and we'll write that here, 17 square root of 2 all over 2. So that's the exact value. We could get a decimal, but that's the exact value. So if you know your 45, 45, 90 triangles well, then you know if side B is 17 square root of 2 over 2, that means side A is the same. So they're both the same length, so 17 square root of 2 over 2 for both little a and little b here. And we're done with this lesson.